Hi everyone, I would like to present the results of our recent work in characterizing coherent emission from relativistic magnetized shocks with applications and implications for FRB models based on blast waves based on shocks. And the picture we're working on is the picture in which alpha waves launched from the magnetar surface may become nonlinear in the magnetosphere and eventually dissipate their energy at a blast wave that propagates in the surrounding magnetar wind. The properties of the shock that is produced, this is shown by simulations by Yager last year. The shock is ultra-relativistic with the Lorentz factor much larger than unity. It propagates in a strongly magnetized region with sigma, the ratio of the Poynting flux to kinetic energy flux, much larger than unity. And it's transverse or perpendicular, meaning the magnetic field is transverse to the direction of propagation of the shock. These are the properties imprinted by the magnetar electron-positron wind. We are now in the position of characterizing the properties of the coherent emission produced by such shocks from first principles, thanks to fully kinetic particle in cell simulations. And these simulations are telling us that such shocks do produce coherent emission. This is shown in 2 dimensions. There is an initial transient, the shock is silent, quote unquote, for a while, and then it produces again these ripples that propagate into the upstream. This is our candidate FRB. And we can measure the properties of such electromagnetic waves, as I said, from first principles now in 3 dimensions. This is what our recent paper was about. And in particular, 3D is essential to quantify the polarization. We have 2 modes of electromagnetic waves in a magnetized plasma, the X mode with a fluctuating magnetic field parallel to the background magnetic field. The O mode, which may be deteriorating the polarization of the X mode, has a fluctuating magnetic field perpendicular to the direction of the background magnetic field. So with 3D particle cell simulations, we can quantify the importance of the O mode and the X mode. And this is what we find. We find that the ratio of O mode Poynting flux to X mode Poynting flux drops with increasing magnetization as 1/sigma. We do have an analytic model that is justifying the scaling. Bottom line, the polarization degree, which is related to this ratio by 1 minus the ratio of O mode power to X mode power, scales like 1 minus, as written here, 0.8 divided by sigma. So we can get to high polarization degrees at high magnetization, sigma larger than 100. This measurement was done in a broadband sense, so for the entire spectrum of the radiated emission. What this plot shows is that especially for sigma large, the red is the sigma 10 case, there is also a line-like feature at relatively low wave numbers, half of the peak wave number, that is even more pronounced in the X mode relative to the O mode. Here, the O mode spectrum is the dotted line, and it's artificially shifted up by almost 2 orders of magnitude. And you can see that even with this shift, this line still has a dominant X mode component. The overall spectrum shifts up in frequency. This has been well known by our 2D and 3D and 1D simulations before. The 3D is really adding the properties of the polarization. So bottom line, high polarization degrees are okay with the coherent emission produced by shocks as long as we are in the high sigma regime. Ciao.